I'm going to explain Gaussian elimination and how we use it to solve a system of linear equations. To start with, we're going to introduce elementary row operations. Now these are three operations that we can apply to a matrix. Now the three are to swap row I and row j around, and this is denoted using the shorthand notation here, where capital Ri is row I and capital Rj is row j. We can multiply row I by k, and we can also add row j multiplied by k to row I. Now a matrix is said to be in row echelon form if the following are satisfied. So if any non-zero rows are above any all-zero rows, and in each non-zero row, with the exception of the first row, the pivot element is to the right of the pivot element in the row above. Now the pivot element is simply the first non-zero element in each row. Now to use Gaussian elimination to solve systems of equation, we first form the augmented matrix. Now this is a matrix where we have A, which is the coefficient matrix for our linear system, separated by a partition, and then we have B, which is the constant vector. We then use elementary row operations to reduce the augmented matrix to row echelon form, and once it's in row echelon form, we work backwards through the variables, solving in a process known as back substitution. So I show this by way of example. So here we've got a system of linear equations. We have three equations in three variables, x1, x2 and x3. So we first form the augmented matrix. So here we have on the left of the partition we have our coefficient matrix, and on the right of the partition we have our constant vector. So our first pivot is this one here, and to row reduce this to reduce row echelon form, we need the values beneath the pivot to be 0. So to do this, we take row 2 and we subtract 2 multiplied by row 1. Okay, so to get 2 to be 0, we need to subtract 2, and so therefore we need to multiply this 1 in the pivot element by 2. Now we could also do similar for row 3. So we've got row 3, if we subtract 4 multiplied by row 1 from row 3, this 4 will reduce to 0. We can do these two row operations at the same time because they don't affect each other. So the row operation for row 2 does not affect the values in row 3. So if we calculate those row operations, we can see that the elements beneath our pivot with 1 are now equal to 0. So we move to the next pivot. So the next pivot is 5, and we want this number beneath the 5, which is also 5, to reduce to 0. So this row operation is going to be row 3 minus row 2. So this gives me this augmented matrix down here. So here, this is in row echelon form because our pivots 1 and 5 and minus 12, they're all the pivots beneath each pivot is to the right. So for example 5 is to the right of 1 and minus 12 is to the right of 5. So now we have it in row echelon form, we can solve our system using back substitution. So if I write this system in terms of the equations, okay, so essentially converting it back into the equations, we see have these three equations. Now the bottom one is only in terms of one of our variables, so we could easily solve for x3 by dividing both sides by minus 12. So this gives us x3 is equal to 2. Now working back up the system, our second equation is 5x2 minus 2x3 equals minus 19. We know that x3 is equal to 2, so we could substitute that into the equation and easily solve for x2, giving us minus 3. And finally, we now know what x2 and x3 are, so we could substitute these into the first equation. We don't actually need x2 here, but we could have worked out what x1 was just from x3. And using a similar method, we calculate, but the solution for x1 is simply 1.